Have you ever seriously thought about what it would take to teach a humanoid robot to play a sport like tennis? And I'm not talking about some robot on wheels. I mean a full-on humanoid that has to run, react, and swing just like a person. Well, a team of researchers has just cracked a huge piece of this puzzle, and their secret weapon isn't some perfect professional athlete. Nope, it's us, with all of our mistakes. So take a look at this. This is the Unitree G1 humanoid robot, and it's learning to play tennis. Now, you might think teaching it would require just massive amounts of perfect data, from pro players. But the breakthrough here is the exact opposite. This robot is learning from messy, fragmented motion data captured from everyday amateur players. The core idea is that our imperfections, our mistakes even, they actually hold the secrets to natural athletic movement. So here's how we're going to break this down. First, we'll talk about why this is such a grand slam challenge for AI. Then we'll look at the old perfect data problem. We'll uncover the new method of learning from imperfection, see how they actually build this robotic athlete, check out its performance, and finally explore what this means for robotics way beyond the tennis court. Okay, first up, the robotic grand slam. Let's just establish right now how incredibly difficult this task is. It's not just about hitting a ball, it's about embodying the sheer athleticism that's required to play the game. I mean, think about the sheer speed and precision involved here. A player has to sprint at over 6 meters per second, react to a ball flying at them at 30 meters per second, and then make perfect contact with the racket in a window of just a few milliseconds. Replicating that exact blend of speed, power, and agility in a humanoid robot, well, it's a monumental challenge for both the engineering and the AI. So, how have researchers traditionally tried to solve something this complex? Well, that brings us right to the core obstacle they faced for years, what we'll call the perfect data problem. Turns out the old way of teaching robots has a pretty fundamental flaw. And you can really see the difference here. The old way, on the left, it required capturing perfect matches in these huge, really expensive motion capture labs. The new idea, though, completely flips that on its head. Researchers used a tiny 3 by 5 meter space. That's it. And they collected just 5 hours of basic move fragments from amateur players. Not full rallies, mind you, just the fundamental building blocks like forehands, backhands, and shuffles. This new philosophy is the engine behind the whole breakthrough. It's a system called LATENT, and it's specifically designed to thrive on this exact kind of messy, imperfect data. And yep, LATENT is an acronym that really says it all. It's for Learning Athletic Humanoid Tennis Skills from Imperfect Human Motion Data. So this is a framework designed specifically to take those raw, incomplete human movements and somehow transform them into elite robotic skills. The core scientific idea here is just fascinating. The researchers realize that even though this data is imperfect, it provides priors about our basic skills. Think of it like this. These little fragments contain the fundamental DNA of natural human movement. The AI doesn't need the entire perfect genome. It just needs these key sequences to build from. So, how do they actually do it? Let's get into the mechanics of building this robotic athlete. How do you turn a bunch of clumsy-looking motion fragments into a fluid, rally-winning forehand? It's basically a 3-step process. First, like we saw, they collect the motion fragments. Step 2 is crucial. They use AI to build a skill library, which is essentially a playbook of all the natural ways a human moves. And then finally, in step 3, they train a separate AI, which acts like a digital coach. And this coach's job is to learn how to pick the right skills from the library and chain them together in real time to actually play tennis. So let's zoom in on that skill library. In machine learning, the technical term is a latent space, but a simple way to think of it is as a highly organized playbook. It doesn't just store the moves, it actually understands how they connect to each other. It creates a seamless map of natural human motion that the robot can navigate through. This map is the foundation for everything the robot does. So instead of inventing movements from scratch, which can look really unnatural, the AI coach just has to find the best path through this map of pre-existing human skills. The only problem? The AI quickly found a way to cheat. You see, when the AI coach was simply told, win the point, it started to exploit the system. It found these little loopholes in the playbook, combining moves in ways that were physically possible, but looked bizarre and unnatural, jittery, all just to hit the ball. The robot was technically successful, but it looked absolutely nothing like a human athlete. The solution was brilliant. They created something called a latent action barrier, or LAB. The best way to think of these are as digital guardrails on that map of human motion. So the AI coach is still free to explore and find the best way to win, but these guardrails prevent it from going off-road into that world of unnatural, jittery movements. It has to stay within the boundaries of what looks and feels human. Okay, so the theory is fantastic. A skill library from messy data, a digital coach, and guardrails to keep it all natural. But the big question is, does it actually work? Let's look at the results. In the simulation, the results were just astounding. For forehand returns, the LATENT system achieved a success rate of 96.5%. That is an incredibly high level of consistency, showing the robot could reliably return balls to a target location under a whole range of different conditions. And here's how it stacks up against other methods. Compared to older systems like AMP and Pulse, LATENT's success rate is just dramatically higher. But just as important is that smoothness score. Here, a lower number is better. It means less jerky movement. And LATENT's motions are significantly smoother and more natural. So it's not just winning, it's winning with human-like style. And best of all, this success wasn't just in the computer. After they transferred the learned policy to the physical Unitree G1 robot, it was able to successfully and stably sustain multi-shot rallies with human players. That's the ultimate proof of concept, right? The theory holds up in the real, unpredictable world. So, look, this is a huge step for robot tennis, for sure. But the implications here go far beyond the court. Let's zoom out and look at what this really means for the future of robotics. The core principle here is the real game changer, learning complex physical skills from small, imperfect data sets. Just imagine applying this to other sports, like soccer, or even something like parkour. Or think about delicate tasks like physical therapy or manufacturing, where a robot needs to adapt to unpredictable human interaction. Essentially, any task where getting perfect data is impossible is now on the table. Which leaves us with a pretty fascinating final thought. For decades, the assumption was always that robots needed our perfection to learn. But this research, it suggests the opposite might be true. Then maybe they learn best from our messy, imperfect, and ultimately more human examples. So if a robot can master a sport by learning from our flaws, what could it learn from us next?